All right, let's talk a little bit more about. So here we got maximal ideals, and this is a little. I sort of like this stuff because we got Zorn's lemma right off the bat, and so this has a little bit more of an analytic feel to it, and I really like that. So, anyways, just as a reminder, well, then again, I guess Zorn's lemma is one of those things where it's not always taught in a class. There's a lot of times where like you'll get into a class like at some point in your mathematical career, people will assume that you're familiar with Zorn's lemma, but it's not necessarily something that someone will teach you at some point. So sometimes you have to go out on your own and figure out what it is. But basically, Zorn's lemma is a proposition that's equivalent to the axiom of choice. So it's not true or false. It's something that you can choose to accept as part of your foundation of mathematics. And me being an analyst, I really like the axiom of choice. I think it's fine. I don't think there's anything wrong with it. Some people don't like it, and I don't. All right, that's cool with them. I mean, I don't care, but I'm fine with it. I think it's great. So, anyways, what it says is that if we have a non-empty set S, which is partially ordered, which means that we have like an operation or like a relation like less than, that's basically the same as less than or equal to, but it doesn't have to do with size per se. It's just some way of comparing two elements of the set where you say that one is less than or equal to another, and it has to be like obviously you can't have like A less than or equal to B and B less than or equal to C and C less than or equal. Well, if you have that, then that implies that they're all equal. Anyways, if any of this is like unclear, then go look it up on your own. But we have a partially ordered set, so we have a set which is ordered, and there you don't necessarily have to be able to compare every. It's not necessarily the case that for any two elements of the set, one is going to be less than or equal to the other. There needs to be sometimes you'll have one set that's less than or equal to another. But anyways, and we assume that every chain has an upper bound in S. So a chain is just a totally ordered subset. So you'll have like one element which is less than or equal to another element which is less than or equal to another, and so on and so forth. And so then this has an upper bound in S, meaning that given this this chain, there is an element in the set S which is such that every single element in the chain is less than or equal to this particular upper bound. Okay, so if this holds, then S has a maximal element, i.e., there is, when I say maximal element, that doesn't mean that this maximal element is greater than or equal to every single other element, because this is just a partial order. There could be plenty of elements in the set which our maximum element is not comparable to. We don't have less than or equal to in either direction. But what we do have is this maximal element is such that given any other element in the set, either this element is not going to be comparable to our maximal element, or it's going to be less than or equal to our maximal element. Or in other words, if this maximal element is less than or equal to some other element, then that other element is precisely the maximal element. So the only thing greater than or equal to a maximal element is itself. All right, so that's Zorn's lemma. And what we're going to use it for is we're going to prove that every ring has a maximal ideal. So the way we do this is we let this fancy cursive I be the set of proper ideals in R. Observe that this is not empty, because we know that the set consisting only of 0 is an ideal. It's closed under addition and multiplication by all elements in R. And we know it's a proper ideal because we've taken our definition of a ring to not include the 0 ring, i.e. for us, for our purposes, in any ring, 1 is not equal to 0. So, yeah. Right, so we have a non-empty set, and it's partially ordered by inclusion. So if you have any two ideals, it doesn't have to be the case that one of them is contained in the other, but it could be the case. And if so, this inclusion is, it satisfies everything you need for a partial order. And that's something that you can like sort of dig into the details if you want to, if you haven't seen this stuff before. But this is a very typical application of Zorn's lemma, is using ordering by inclusion as your partial order. Anyways, so we want to apply Zorn's lemma, so we've got to check that every chain has an upper bound. So let's take a chain, A1 contained in A2 contained in blah 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 blah, and these are all elements in I. So these are all proper ideals, and we have this containment. All right, so we want to find an upper bound. So let's take their union. So what do we know? We know that for every single j, aj is contained in A because it's part of the union. And so therefore, if this A ends up being an element of I, then it is an upper bound for every element in this chain, and thus it's an upper bound for the chain. Alright, so to prove that A is in fact an element of I, A is an ideal, and that, you can flesh out the details a little more if you want, but basically how it goes is, you need closure under addition. Well, certainly it contains 0, because every one of these contains 0. For closure under addition, if you choose any two elements, say A and B, in this union, which is A, so if you choose any elements A and B, then A must be contained in some AI, and B must be contained in AJ for some indices I and J. And then you take, maybe I and J are the same, but if not, then you take the bigger one, and because this is a chain, the larger index will contain both A and B. And also that larger index will, A subscript that index will be an ideal, and it contains those two elements, and so it will contain their sum. And so this is closed under addition. And then if you take any element and multiply it by any element of R, then it's the same thing. You take any element in here, then it's going to be an element of AI for some I. And since AI is an ideal, multiplying the element in here by any element of R will keep you in that particular AI, and thus you will stay in A as a result, and therefore A is an ideal. Furthermore, A is not equal to R, and this there's sort of a quick way to see this, but it's not entirely obvious at first. This is not equal because if A were equal to R, then R always contains 1, so that would mean that 1 is an A. But because A is this union, that would imply that there is some that 1 must be contained in AJ for some J. But if AJ contains 1, it's an ideal. So ideals that contain 1 are the whole ring, and so then AJ is R. But this contradicts that this is a chain in I, meaning that each element of this chain is a proper ideal. So this not being a proper ideal would contradict it being a proper ideal. And so we have a contradiction, and so A is not equal to R. So in fact, A is a proper ideal, and it therefore is an upper bound in I for this chain. And right, so A is an upper bound for the chain. And this holds for every single chain. Every single chain has an upper bound. And therefore, we've satisfied the conditions of Zorn's lemma. And so applying it allows us to say that I has some maximal element M. And obviously, M must be here when okay, so I'm sort of using maximal in two different ways, but it ends up being the same. But you sort of have to argue that it ends up being the same. So I has a maximal element M. What I'm saying here is that M is such that if you take any other element of I, say n, if you take any element n in I, then either n is going to be contained in M, or n is not going to have any relation with M. It's not going to be the case that M is contained in n, or if that is the case, then n would be equal to M. All right, so that's what it means to say that this is a maximal element. But then that means that any ideal between M and R, well, if you take any ideal that is between M and R, it could be R, and that's fine. And if it's not R, then it's an element of I. And so then either it's not comparable to M or it's contained in M. Well, we know that it is comparable to M because we assume that it contains M, and therefore it's contained in M, but that means that it is M. So, therefore, M is a maximal ideal. So there are a few more details there that I didn't write out, but basically what I'm saying, I has a maximal element with respect to the partial order implies that this maximal element is a maximal ideal in the ring. All right, and that's that. So it turns out we don't really, well, I guess we do use this a lot. Like, this fact is useful, but you don't really use the proof itself a lot. The proof is, there's not really a lot of other proofs. Well, there are some proofs in ring theory that use sort of Zorn's lemma type arguments, but anyway, this is one of those where the proposition tends to be more important than the proof. But anyways, moving on, we have a corollary of this. If we have a proper ideal of a ring R, then there is a maximal ideal of R which contains this ideal A. So here this A, this is just a proper ideal. We don't know anything about it being maximal at all. But we have a maximal ideal containing A. And the way we do this is we basically combine this proposition. We apply this proposition to the quotient and we combine that with the isomorphism theorems. And like if you understand this proposition and you understand the isomorphism theorems well enough, that should be enough for you to be like, oh, I know how I could prove this if I had to. But when you write it out, there's actually a lot of details once you start unpacking it. Well, there's not that many details. Anyways, let's start going through those. So we have R mod A is a ring, obviously, because A is an ideal. And so by our proposition, it contains a maximal element, and we'll call this M bar. And we use the bar just to specify that it's in this quotient ring. All right, so if we have some ideal N bar in R mod A, then if it's the case that M bar is contained in N bar is contained in R mod A, well, obviously this holds. If this holds, then either N bar is going to be equal to M bar or N bar is going to be equal to R mod A, because that's what it means for M bar to be maximal in R mod A. Okay, so now we know by the isomorphism theorems that the ideals in R mod A can be written as taking ideals in R and then quotienting them by A. So we have this maximal element M bar of R mod A, And so there must be some ideal M which contains a... Oh, I think I misspoke there. Right. It's not only that ideals in R mod A are quotients of ideals in R, but it's that quotients or ideals in R mod A are quotients of ideals in R which contain A. And that's important because if it doesn't contain A, you can't quotient it. It doesn't make sense. So we know that there is some ideal M in R which contains A, which is such that M bar is just what you get when you quotient M by A. All right. So now what happens in R? Suppose we have an ideal N in R such that M is contained in N is contained in R. Then we basically move this into R mod A to prove that M is maximal. So this inclusion implies that when we just quotient everything by A, we get M bar is contained in N bar is contained in R mod A. And since M bar is maximal, this means that N bar is either going to equal M bar or it's going to equal R mod A. But now we move back into R, and so we have, let's see here, either N is going to equal M when we bring it back into R, or N is going to equal R when we bring it back into R. Okay, so what have we proven? For any M is an ideal in R which contains A and is such that for any ideal N, if M is contained in R is contained in M is contained in N is contained in R, then either N is going to be M or it's going to be R. And that's what it means for M to be a maximal ideal. And it also contains A. So therefore, we have shown that there is a maximal ideal of R which contains A. And this holds for any ideal A. And so given any, proper ideal. So given any proper ideal, there is a maximal ideal in the ring which contains that proper ideal. And that's what we wanted to prove. And that's all that we have to say for now about maximal ideals.